We'll continue on this calibration theme. Second talk using similar algorithm presented by Tobias from Northwestern University.
So I'm Tobias Holden. I'm a graduate student at Northwestern. I work with Dr. Jillian Jardin, and I'm really happy that you all have had the same introduction to these methods that I got from Aurelian. So we're more or less on the same page. I'm going to talk about our framework for using Bayesian optimization to recalibrate EMODs within host malaria model. I think people have the gist unless you just entered the room, but a little bit about what we mean specifically by calibration is fitting our model outputs to data to infer the values of some unknown model parameters. Like Aurelian mentioned, these may be unknown because they're actually impossible to measure or because the experiments that would reveal them are too costly or unethical. And we ideally do this using reference sites that have high quality data on transmission and at least one other epidemiological outcome of interest. In our case, we also try to use a mix of older data sets and newer data sets, the older ones capturing something about the natural history of malaria in the absence of interventions, and newer data sets that give us more info on how the context has changed with interventions, maybe higher quality measurements or new diagnostic tools. So the motivation here really is that we want our model to capture and reproduce real life disease metrics, as I've just said, in order to explain things in a way that we think is sound and maybe even make some interesting predictions. And specifically with EMOD, some problems with our within host model, or room for improvement, I guess I should say, are that we've noticed that the model tends to over-attribute onward transmission of malaria to symptomatic cases or cases that were at once symptomatic, and that doesn't really square with recent literature on the contributions of the asymptomatic reservoir. And then secondly, and I'll talk a little bit more about this later, but we see a sudden and sort of paradoxical rebound in clinical incidence after mass drug campaigns, things like seasonal malaria chemoprophylaxis or a mass drug administration, where the incidence in the model after the drug campaign is actually a lot higher than without giving the drugs, and that's not how we think things work. What makes this difficult? Aurelian gave a great overview, but just to reiterate, the complexity of models like EMOD or open malaria means that sometimes we're looking at long simulation times. I think Aurelian said something on the order of 10 minutes. Anyone who works with EMOD knows it can be a little bit longer, on the order of hours. And there are a large number of unknown parameters as these equations have been built up over time and linked. The curse of dimensionality, we're looking at 17 parameters here. My fun fact about 10 to the 17 is that on Wikipedia, it says that's the estimated order of the number of mosquitoes on Earth. So not stars in the universe, but a pretty cool number. And again, as Aurelian so awesomely described, when you're dealing with such a multidimensional space and you have a complicated set of outputs with nonlinear relations, this irregular goodness of fit space provides a lot of local optima for your algorithm to potentially get stuck in. And so an iterative search strategy or just randomly searching forever is very unlikely to yield the best fit. How do we do this? We have the overall goal of finding input parameters, which I'm just going to be calling X, that best fit our reference data and optimize our outcome Y. So if you think of it just as a non-parametric function, Y as a function of X, and we want to find the X to optimize Y. In our case, we are varying 17 configuration parameters in the model that are related to immunity, symptoms, and transmissibility of infections in the human. And I just have a little diagram of the EMOD, a little overview of EMOD on the right there. You can see some of the parameters that are under calibration. I won't go into too much detail about them, but if you're curious, the red ones are ones that have been added this go round compared to prior calibrations of EMODs within host model, because we thought that they may have some effect on how well we could fit our reference data. The reference data that we're trying to capture and fit are across various types: incidence versus age, prevalence, distributions of parasite and gametocyte densities, and infectiousness to mosquitoes based on gametocyte density. And these are coming as a mix from trial data from 8 sites across sub-Saharan Africa. And so we have not just different types of data that we're trying to fit, but data in different locations. And you kind of have to come up with a way to consider all of these things together. How much do you value one objective versus the other? I think in the previous talk, we saw the example of taking a weighted sum of errors between your simulation outputs and data. In our case, I don't have a great word for it. Maybe someone already knows a word for it, but I'm calling it the harsh critic. Basically, we run simulations that represent each of these reference sites where data come from. We compare the simulation outputs using a new set of parameters I to the fit using I'm calling them default, but the parameter set that was identified in previous calibrations that we're currently using in Emod. And wherever the simulation parameter set performs the worst, that ratio is what it's assigned as a score. So just as an example, if we had a parameter set I that performed equally well on all of the objectives and all of the sites, except for in one site, incidence was 2 times worse, then its score would be 2. So a better score throughout the rest of these slides is a number below 1, and a worse score is a higher number. And we can talk about that choice maybe if I have time for questions. The overall framework for how we're doing this is based on the paper by Teresa Riker et al. And again, with lots and lots of support from Melissa Penny and Aurelian. Wouldn't be able to do this without them. And we go through this cycle of 3 phases, essentially running the very expensive and time-consuming Emod simulations, then training and using a Gaussian process to emulate our simulator as a surrogate model, and then using a strategy to sort of continue on through the search in parameter space, making efficient choices about where the next round of simulations should be. So the simulations are tuned to match conditions at each of the reference sites. They're coming from diverse places that each have their own seasonality and history of transmission intensity, whether or not there's been interventions like antimalarial treatment, and actually even the sensitivity of the diagnostics that were used to arrive at each of the data sets. These are tuned in the model. And then we plug in our parameter sets. Initially, in the training phase, these are randomly selected. Later on, they're intelligently selected. And run some Emod simulations, which really is the slow step in this process. I love snails, but they're slow. Then for each simulation, we score the goodness of fit across all sites and objectives. And as I mentioned, it's essentially you're scoring the relative likelihood that the reference data and the simulations come from the same distribution. And then we're just taking the worst sort of single site objective score to assign to each parameter set. So there's just a single scalar as the score based on how bad you are at fitting the objective that you're worst at. So as I said before, better is below 1, worse is above 1. Oh, then we move on to emulation. The idea here, the motivation is that this emulator, the Gaussian process model, is much, much faster to evaluate than running Emod simulations. And so in between each round of simulations that have actually been run, we emulate that posterior distribution at 5,000 additional candidate parameter sets, many more than the 100 that we run at each batch. Oh, apologies. Okay, then after producing that posterior distribution and having an updated idea based on the observed simulation outputs of how other parameter sets will perform, we use the same trust region-based or turbo Thompson sampling algorithm to kind of balance exploring new areas of the parameter space versus exploiting near the best observed optimum so far. And this cycle continues going through simulation, emulation, and acquisition. And the results I'm going to show today for 40 cycles until 5,000 actual simulations have been run and scored. And then we finish. So is this working? Is it doing anything? We're a little newer to using this process in our group, so I want to talk about how we know it's doing what we want. On the one hand, one of our motivations is that this should speed things up. And you can see on this plot, on the x-axis is the batch or sort of cycle number that we're in. The y-axis is the time it takes for this step to finish. The blue line is fitting the Gaussian process model. And this is essentially on the order of 20 minutes at the longest by the end of this. Emod simulations I'm not showing on this plot because they're quite a bit longer. I apologize for not updating the text on the right side. Those time estimates really are dependent on what else is going on our cluster, but it's an average of 1 to 2 hours per simulation. So this is, at least for now, able to move things along a little quicker. You can see that this time complexity increases cubically. And so, especially if we were to actually explicitly represent multiple outputs instead of compressing everything down to that one harsh critic score, running this for much, much longer, we might sort of pass the point where it's saving us time to fit the emulator. but for now it's great. And what's going on during all that time? The parameter search is converging on what the model observes as the region of best fit. And so we have our 17 parameters, a subplot for each one here. The y-axis is not so important, but you see over time with successive batches, the algorithm forcibly converges on a new area of best fit. The dashed lines are the values for each of these parameters in the previous calibrated parameter set. So some of them are quite similar, but others have deviated quite a bit. We really want to see if those differences are making any qualitative difference on the back end. So just kind of cycling through what a process, the latest run of this process looked like. I'm going to be showing visualizations here where the sites that the reference data come from are the locations on the x-axis. The y-axis is the score for the simulation's parameter set y. That's its worst performance on a given objective, but you'll see the performance on all of them. And then the dashed line in the middle is the just kind of baseline. We're referencing the previous calibration. So to start off, the target for improvement, as I've said, I think 3 times now, would be below 1. And so we start off with 1 round of 100 randomly selected simulation parameter sets, and this is the best one that came out of it. You see that many of these bars are above the team default or the prior baseline. But as we step through, you can see how things improve with that ceiling representing the worst score of the whole parameter set getting pushed down over successive rounds. Doing great. I didn't mention that the color for each of these bars is the particular objective that you're seeing the score for. And we keep pushing along, and I hope you're all holding your breath. Or actually, I guess I hope you're not holding your breath, because as of right now, under the current setup, no new parameter set has been found that improved on all of our objectives. I think you can see that there are just a few remaining that are within 5% of the previous benchmark. And many of the other objectives have improved pretty much across the board. Gameta site density, the blue bars. Others are like infectiousness. The purple bars are more or less where they were before. And this might be due to the way that we've set up our search strategy. If we're a little too decisive about committing to shrinking the search space, getting stuck in a local minimum. It could also just be that this strategy of trying to minimize the worst performing objective versus, say, the sum of residual errors or something else is getting us stuck here. And then also just because this is all benchmark against the original or the previous calibrated parameter set, some of these objectives were already fitting well and others not so well. And so this is something that I'm at least still thinking about. But I'll just show you here. The black points on each plot are the reference data. The gray line is the prior calibrated parameter set, and the pink line is sort of the results of the best so far. On the left, we have incidence versus age from 2 sites. Top right corner is prevalence distribution versus age, 1 site. And then this bottom right corner is the density of Gameta sites by age and by month. I'm only showing the results for children aged 5 to 15. But just to see that, a lot of work has to go into, like Aurelian said, having high quality data, but also representing that data properly when you set up the comparison, right? So it's only going to fit as well as I've sort of prepared it to. And it's worth talking about. We have 18 total objectives. I'm showing part of 3 of them here, or 4. So we'll really be digging in and taking a look at whether, despite the fact that on the score, none of the parameter sets have been better, maybe this one, we're happy with the fit to objectives qualitatively. A little more info. Aurelian just briefly mentioned this, but the Gaussian process model that we fit has a hyperparameter called the length scale, which gives us a little bit of information about the correlation between the parameters and the objectives. Here, just as an example, I'm showing 2 and their correlation to that overall score y. A shorter length scale, like we see on the left for the parameter antigen switch rate, is you could think of that as a strong influence, and a larger length scale, like you see on the right, is a weaker influence. And when we look at these in kind of a heat map, in this case, a darker red color is a more influential parameter. Darker black color is less influential, white kind of in the middle. And fitting a separate Gaussian process to each of the objectives on the y-axis here, we can see that, as we might expect, parameters that are associated with immunity are quite significant for many of the objectives, whereas symptoms and infection maybe play a bigger role in incidence. Some of the gametocyte or transmission-based parameters really affect gametocyte density and infectiousness, but less so others. And so we start to see relationships that make sense. Just really quickly talk about some next steps to validate and extend the framework. We want to assess the calibration or the performance of the recalibrated model against data sets that it didn't see during the fitting process. Some of these would be actually objectives that we haven't even explicitly fit to, like infection duration or peak gametocytemia and parasitemia, severe disease outcomes, but then also incorporating new data sets that we think will help us address that issue I mentioned at the beginning of not really capturing the contribution of asymptomatic infections. That's what this third site here in Sapone, Burkina Faso is all about. And then finally, I mentioned that we have this sort of paradoxical rebound after treatment, and I haven't really addressed that. One of our plans for addressing that is using alternative innate immune models that include heterogeneity. Showing you here, this is a plot of a simulation where children under 5 were given mass drug administration called SMC. The purple trace is for the sort of null situation where this mass drug administration did not happen. And the teal line is after SMC, delivered here in July or August, I guess. And this is the paradoxical rebound that I was describing, where actually doing this mass campaign results in more a higher instance and more cases overall than not doing it, which is not what we think should be happening. So quickly, I'll just say that there are other models that exist in EMOD. You can add heterogeneity based on age or just inter-individual variation in the sort of threshold at which that immune response kicks in and the strength of that immune response in clearing parasites. And this, I don't want anyone to look at it for too long because it's definitely wonky, but the only point I'm really trying to make here is that using the parameter set from the prior calibration of EMOD gives you a wildly different result when you change this innate immune model. So if you sort of flip the switch on a setting that is there in the model, you might see changes that you weren't expecting. In conclusion, calibration is important. It's difficult. This Bayesian optimization framework makes it a little bit more accessible and can accelerate it without necessarily sacrificing your ability to fit any of your target objectives. Can also help you see relationships between parameters and outputs, and really the underlying changes to the model structure, whether that's something like an alternative innate immune model, adding really any change in the model structure you would like to be able to perform a recalibration and just check, has this significantly changed the values that I need to supply for my unknown parameters? So that is, I think, everything. I want to thank some special people, both at Northwestern, Swiss TPH, IDM, University of Western Australia, all over the place for helping with this, and then the people who have been funding me as a PhD student. Thanks.